Welcome to this detailed walkthrough of a machine learning project designed to predict the age and weight of abalones based on their physical measurements. The seafood industry relies on accurate weight and age estimation for sustainability, pricing, and efficiency. Traditionally, determining abalone age involves slicing the shell, staining it, and counting growth rings under a microscope. This process is labor-intensive and costly. By leveraging machine learning, we can create an automated, accurate, and scalable approach that replaces this manual process. The goal of this project is to build predictive models using a variety of regression techniques. We will follow a structured approach, covering data acquisition, preprocessing, exploratory analysis, feature selection, model training, validation, performance evaluation, and feature importance analysis. Determining the age and weight of abalone is critical for fisheries to ensure they are harvested at the correct time for maximum yield and sustainability. The industry currently faces three major challenges. The first challenge is scalability, as the manual age and weight estimation process is slow and cannot meet growing demand. The second challenge is sustainability, since overharvesting younger abalones leads to population depletion, which disrupts ecosystems. The third challenge is operational costs, as manual measurements require significant labor and equipment, increasing costs for farmers and processors. A machine learning-based solution can automate abalone age and weight prediction using easily measurable attributes such as length, diameter, height, whole weight, shell weight, and viscera weight. This allows faster sorting, optimized pricing, and sustainable harvesting. To begin, we import the necessary libraries. This project uses pandas and numpy for data manipulation, seaborn and matplotlib for data visualization, and scikit-learn for machine learning models. Additional libraries such as PyCaret, XGBoost, and LightGBM are used for automated model selection and boosting techniques. The AutoVis library is also incorporated for exploratory data visualization. After importing the libraries, we fetch the abalone dataset from the UCI machine learning repository. The dataset consists of 4,177 samples, each containing 8 numerical features and 1 categorical variable. Before building models, we analyze the dataset to understand its structure, feature distributions, and relationships. First, we check for missing values. Since no null values are found, no imputation is required. To identify strong relationships between variables such as length, diameter, whole weight, and shell weight, we construct a correlation matrix heat map. Box plots and histograms reveal outliers in weight and ring count, which could affect predictions. To further assess the numerical characteristics of the dataset, we check for skewness in the distribution of numerical features. A skewness test allows us to identify whether the data is normally distributed or if it has a right or left skew. Features such as whole weight and shell weight exhibit significant skewness, indicating the presence of extreme values. This step informs how we handle transformations and whether techniques such as log transformations or outlier removal are necessary. To better understand the numerical characteristics of the data, we compute basic statistics, including mean, median, standard deviation, minimum, and maximum values for each feature. This helps us identify any unusual distributions and informs preprocessing decisions. Certain attributes such as whole weight and shucked weight exhibit a wide range, reinforcing the importance of scaling before model training. The categorical variable sex, which includes male, female, and infant categories, is then encoded using label encoding. This transformation converts categorical values into numerical form so they can be used effectively in machine learning models. After encoding categorical variables, we analyze outliers in more detail. Outliers can distort predictions, especially in regression models that rely on continuous numerical features. We apply a combination of box plots and interquartile range (IQR) analysis to detect extreme values. Features such as shell weight and viscera weight contain significant outliers, requiring either capping with winsorization or transformation using log scaling. These methods help in reducing the impact of extreme values while maintaining useful information in the dataset. To ensure our models perform optimally, we pre-process the data using scaling, encoding, and outlier treatment. Because features have different scales, we apply standardization and min-max scaling to bring them into a uniform range. The dataset is then split into 80% training and 20% testing, ensuring an unbiased evaluation of model performance. Before selecting models, we conduct a feature importance analysis to determine which features contribute the most to abalone weight prediction. Feature importance helps identify the most relevant predictors, allowing us to remove redundant variables and improve model efficiency. Tree-based models such as Random Forest and XGBoost provide built-in feature importance scores. The analysis reveals that diameter, shell weight, and whole weight are the most significant predictors. This confirms that larger abalones naturally weigh more, reinforcing domain knowledge about the relationship between physical measurements and weight. Visualizing feature importance using bar charts allows us to rank predictors in order of relevance, helping optimize future modeling decisions by removing redundant or less influential features. To identify the best machine learning approach, we train multiple models. Multiple linear regression serves as the baseline model, assuming a linear relationship between features and abalone weight. This model provides interpretable coefficients for feature impact analysis. Logistic regression is used to categorize abalones into young, mature, and old based on ring count. This helps understand feature importance in distinguishing age groups. Decision trees provide rule-based predictions, while random forests aggregate multiple trees to reduce overfitting and improve generalization. Ensemble learning techniques such as XGBoost and LightGBM further enhance model performance by sequentially correcting errors, improving accuracy. Finally, a multi-layer perceptron captures complex feature interactions but requires hyperparameter tuning for optimal performance. To assess model performance, we apply cross-validation and evaluate the bias-variance trade-off. K-fold cross-validation divides the dataset into multiple training and validation subsets, ensuring that every observation is tested at least once. Analyzing the bias-variance trade-off helps determine whether the model underfits, meaning it has high bias and oversimplifies relationships, or overfits, meaning it has high variance and memorizes training data rather than generalizing. Linear regression models tend to have high bias, while decision trees have high variance. Random Forest and XGBoost balance bias and variance, making them the best options. To compare models, we use multiple metrics. R-squared measures how well the model explains the variance in abalone weight. Mean absolute error indicates the average difference between actual and predicted values. Mean squared error penalizes larger errors more heavily, making it useful for identifying extreme prediction discrepancies. After training and evaluating all models, Random Forest and XGBoost deliver the best performance. These models accurately predict abalone weight while generalizing well to new data. From a business perspective, deploying this model could revolutionize the seafood industry. Instead of manually measuring abalones, processing plants could simply input length, diameter, and shell weight into an AI system, which would instantly estimate the weight. This could enable real-time sorting, automated pricing, and sustainable harvesting. Although the model performs well, there are potential areas for improvement. Advanced neural networks could improve prediction accuracy, especially with more data. Explainable AI techniques, such as SHAP values, could enhance interpretability, showing how each feature impacts predictions. The model could be deployed as a Flask or Fast API application, allowing seafood companies to input abalone attributes and receive instant weight predictions. This project highlights the power of machine learning in solving real-world regression problems. We covered data acquisition, preprocessing, feature engineering, model selection, validation, feature importance analysis, and business applications. The insights gained here are applicable not just to abalone prediction, but also to agriculture, manufacturing, and other industries relying on biometric forecasting. If you found this analysis useful, consider applying similar techniques to your own machine learning projects. Thanks for watching, and I look forward to seeing you in the next session.